Hey, today we're talking about working with matrices or two-dimensional arrays in C and also in C++. And we're going to talk about some of the annoying things that you really need to keep in mind when working with them. Hey, welcome back everybody. Today we're talking about arrays, specifically two-dimensional arrays, or sometimes we call them, call a two-dimensional array a matrix, because you can't program very long before you're going to need a two-dimensional array in one of your programs, and because they can be a little weird, or let's say that there are some things that you need to keep in mind when working with them that sometimes trip people up. Today's video is definitely going to have source code in it. We're going to be creating source code, and as always, the source code from this channel is available through Patreon. Also, that's where you can get access to my Discord server and my monthly office hours. And all of you wonderful patrons out there who support this channel, thank you. Now let's jump into the code. Okay, so now today we're looking at 2D arrays. Just to make sure we're on the same page, this is an array data structure, but instead of just having a single row of data, you're looking at something that looks more like a table like this with rows and columns. So you have a bunch of different cells. Basically, it's like a table, it's like a spreadsheet, and those cells can contain just about anything. For simplicity today, I'm just going to store numbers, but they could be strings, pointers, structs, really whatever you want to store in a matrixy sort of way. So in this program, I'm starting with a pretty empty program here. Let's just start out by trying to figure out how many rows and columns we want. Let's define a couple of variables here, or constants, I should say, matrix rows. And let's just say let's keep things small. We'll make 5 rows and we'll make columns, make a columns constant, and let's make that 4, okay? So this is just going to define what size I want my matrix, for starters, help us avoid magic numbers. And then we can come down here and we can just declare our matrix like this down in main and say something like int matrix rows and columns. And you notice that this is going to be a lot like a 1D array. Like if it was a 1D array, I would just leave this off. This would just be a one-dimensional array, a list of integers. But if we want 2, we just add a second set of square brackets like this. And so we're basically saying this is the number of rows we want, this is the number of columns, and this is the type that each of our cells in our little table here is going to be. Now, as we're moving into this, you probably want to think about this as an array of arrays. Okay, so the matrix is going to be an array of rows, and each row is an array of ints. Okay, so that's pretty straightforward, but you want to make sure that that makes sense, because all the stuff that follows in this video could get really confusing if that's not really making sense to you. Okay, so now that we have declared this is a local variable that's a matrix, now that we have it, let's say we want to access an element in the array. This is really straightforward. We can do stuff like this. We can say matrix row 0, column 3, and let's say we want to set that equal to 12. And that's pretty straightforward, no surprises, nothing annoying. And if this was really all there was to it, then I wouldn't even have bothered to make a video, because this would be really easy. But of course, we're going to dig a little deeper. So let's take this a little bit further, and let's rather than just setting individual elements of our array, let's go ahead and try to set all of them. So let's do this with for loops. And so we'll just say int row equals 0, row is less than matrix rows, and row plus plus. Okay, so this is basically going to count up. It's going to use a counter to count up by row. I'm using row as the name of the counter. And then let's just do another one that's going to count up by columns. Often you're going to see people use I and J for these, and you'll see me do that at some point. But today I'm just using row and column, just so you can make sure you keep track of what we're actually doing with these variables. And then because we're going to look at how this is stored in memory, I want to actually store something. I could do something simple like just say row and column, and I could just have some number, and it is going to be a number. What I'm going to do here is I actually want to store this encoded in a certain way so that we can look at it later on. So what I'm going to do is I'm going to just take the row number and I'm going to shift it left by 16, and I'm going to OR it with the column number. Okay, now what am I doing here? I don't really want to confuse anybody, but what I'm doing is I just want the value, when we look at it in hexadecimal, I want to be able to clearly see the row and column number, so you can see how the compiler is laying this out in memory. So like I said, I don't want this to confuse anybody, so let me just explain what I'm doing. Is the idea here is that let's say that my row variable is 4 and my column variable is 3, then all I'm doing here is shifting shifting the row variable left 16 bits. So its hex representation looks like this. And then I OR it with my column variable, which is 3. And so the resulting hex value is going to look like this. And that's going to be really handy because now if we just look at the matrix in memory, we'll be able to see how it's being laid out. We'll be able to see what's being stored there. And I think that'll be helpful. So let me show you what I mean really quick. Okay, so let's save it and let's come down and let's compile our code. I am using a very simple makefile here. I'll show you really quick what this is doing. I've got 2 example programs, matrix and matrix 2. One is in C, one's a CPP file, and we'll get to that a little bit later. But you can see our code compiles just fine. And then if I come in here and run this program I've been working on, this matrix program, well, it's okay. It doesn't do anything. It compiles, but that's because I didn't tell it to do anything. So let's jump back in. Sorry about that. And I will come in here and let's just start out by printing out the size of our matrix, because that's something I want to look at as we go through here. So the size of matrix is going to be, we're going to use LU because it is unsigned and it's long. And then let's just use the size of operator and get the size of our matrix. Okay, so now let's come back and compile it. And we'll run it. And okay, so you can see we get 80, which this makes sense because each int is 4 bytes and we have 20 of them. So 5 by 4, so that's 80 bytes, right? Now I want to show you how things are laid out in memory. So I'm going to use LLDB, my debugger, and we'll just run our matrix program in the debugger. And I'm just going to set a breakpoint on line 17 right here where my printf is. And let's just run it to that point. Okay, whole point is just to get you into memory so we can look at it. And now I want to actually look at the memory. Now, like I said, I'm doing this in LLDB, though nearly any debugger is going to have some way to look at memory. And I have a video, a pretty old one, that shows you how to do this in GDB. But in LLDB, we're going to do it slightly differently. So we're going to use the memory command and read, saying we're going to read memory. And then we have a couple different options. We're going to use -s, which is going to tell us the size of the chunk that we want to look at. In this case, because I'm looking at ints, I want to look at them in chunks of 4 bytes. And the format I want to use is hexadecimal, that's X, so this F option. And then the count, how many of these integers I want to look at, and we want to look at 20. So basically we're looking at 20 integers. And then we tell it where to start. We want to start with matrix. So the address where matrix is located, that's what we want to look at. And so this is just going to help me see how memory is laid out. And you can see here that it shows our addresses over here on the left. So this is the address, the location in memory where it is located. And then our values are over here on the right. This is what's actually in memory. So it's a lot like a hex editor. We've talked about that also in previous videos. And hopefully now you can start to see why I use that little encoding scheme. Because you can see when you look at the first entry here, you can see this is row 0, column 0. This is row 0, column 1, column 2, column 3. And then over here, you can see the row number goes up to 1 on each of these. So you got 1, 0, 1, 1, 1, 2, 1, 3. And so you can just see how it's getting laid out in memory, starting at the beginning address and just being laid out in a grid like this. Although in memory, we see it here as a grid because that's how the debugger is laying it out. In reality, this is just like a big sequence of 1s and 0s. So this happens to be laid out in a line. Okay, so that's pretty straightforward so far. Hopefully that's helpful to actually look at it and to see how you can examine things in memory. But now what I want to do is to look at what happens if we try to pass this array to a function. So let's come up here. What I want to do is to make a new function. And this function is going to print out our matrix, right? It's going to print out matrices. And let's start by just passing in a matrix. I'm going to use so MAT is going to be my name. And let's just say we would pass in a matrix, the size that we've been working with like this. Okay, so I just say, hey, print matrix, you get 1 argument and it happens to be a matrix with 5 rows and 4 columns. And this is really a simple case. So let's say we know what size we're dealing with. It's the only size matrix we're ever going to be working with. So we can do this, okay? And now inside we're going to have another, I'm just going to copy these, another pair of nested for loops. One thing when you are working with multidimensional arrays, hopefully you are okay with nested for loops because they're going to come in a lot. But so basically what we're going to do is we're going to loop through our array, and then right up here at the beginning before we start, let's add a printf here. This is going to print out the line number, so the row number I should say, not line. So So we're going to print out the row so that way you can see in the output which row we're looking at. And let's just to format things a little better, let's add a tab character right there. And then each time through for each element, we're going to print that out as well. And this, let's just use %x because we like hexadecimal, and a space. And then let's just print our row and column value for our matrix. Okay, now one last thing, when we're all done with the row, we want to create a new line because otherwise it's gonna get all jumbled up, but this should be pretty straightforward. And then once we have this function, we can come down here in main and let's add one more thing. Let's just say print matrix, and that should work. Okay, so, but just to make sure, let's get out of our debugger down here. Let's compile it. And if we run it, you can see, sure enough, we get the same output that we saw in the debugger with slightly different formatting. Basically, we're just missing some zeros, but the numbers are the same. So this is still all really easy, but at this point, there are bound to be some complaints. So the first thing that people are going to say is they're going to be like, wait, Jacob, but arguments in C are passed by value, right? And so does this make a copy of that matrix every time you pass it to the function? And isn't that inefficient, especially if we were dealing with big matrices? And that's a really good point. So let's try to address that concern first. So I know we just jumped out of our debugger. Let's jump right back into our debugger. And I'm going to break at main. And then I'm also, let's break up here at print matrix. So I'm going to stop in both places and then we can run. This is going to stop us in main. Now, why I wanted to get in here is I just want to look at what's happening. I want to try to understand what's happening when we pass this argument. And so first of all, let's just print out the value of our matrix. So this is going to show us actually well, it looks like it tried to give us the contents of the matrix. I'm actually taking a moment to figure out what the heck it actually produced, but that's not what I wanted to look at anyway. We'll have to come back to ULDB and figure out what's going on. What I wanted to look at here is to print out the address. Okay, so I want you to remember this address. Keep track of this in your mind. This is this, we'll just look at the end, BFF1D0. This is where our matrix is stored in main. Okay, now if we continue on, now we jump into our print matrix. And if this were copied, we'd have a different address. But let's just do, if we print matrix up here, there's a couple things that are interesting. Notice that it didn't try to go through and give me a bunch of elements. It just gave me an address, and you notice that that address is identical to what there was down in main. You notice that the addresses here are the same. And so I know that C uses pass by value, but in the case of arrays, it sort of cheats and treats an array like a pointer, which basically gives you pass by reference semantics, unless in your mind you remember that arrays and pointers are almost the same thing. And I have a video on that if you want to refresh, put that link down in the description. But if you think about it that way, then it makes more sense. And we can argue about whether they're cheating or not, but we can say that this is still pass by value. It's just treating the array as a pointer and passing the value of the pointer. And so anyway, that's going to be efficient. It's going to be fast. It's not copying this whole array, although the whole array pointer thing may be confusing to some people. Okay, so now let's look at another objection. And that is that this code only works for a particular size of matrix. Like it only works if every matrix that I'm ever working with has the same number of rows and columns. And most of us programmers, when we are writing code, we often want our code to be general. I don't want to have a dozen print matrix functions that each handle different size matrices. I want just one that I can use for any kind of matrix. So what do we do in that case? Well, we do have a few options. One option is to pass in a variable length array or VLA. Let me show you how this works. Is I can add here, I can say int rows and int columns. And then here I can basically replace this with rows and cols. Okay, and then here I would have to say rows. This would be cols. Okay. Now with my current C compiler, this is going to work, right? I pass in the dimensions and then I just say, hey, I'm also passing in an array that has those same dimensions. And this is going to work. So if I come down here in main, I can change my call a little bit here. I got to now pass in the dimensions. But now we should be okay. Now, one thing I do want to point out is if you're doing this, you need to make sure that the rows and columns basically come first. And the reason is that if I put the matrix first, then the compiler is going to complain saying it doesn't know what rows and cols are because they've not yet been defined. So we have to define those first in the argument list before we can use them. But now this should compile. Let's just make sure. Let's come back here and compile it. Okay. And it should run. And at this point, some of you are probably saying, cool. And others are saying, what? C can do that? And before you get too excited and run off and start converting all of your code to use variable length arrays, hold up, because I want to just let you know I almost never actually do this. And that's because there are a few really annoying things about VLAs. So the biggest one to me is that since C11, VLAs are an optional feature. So yeah, you heard me correctly. Compilers don't have to support VLAs, which of course seems to defeat the purpose. In my opinion, I mean, the whole point of having language standards is so we know what we can expect from any compiler. And so while this C compiler handled VLAs just fine, and your compiler might handle VLAs just fine, the next one I use or the one you're using might not, and that's really annoying. Now, my second complaint is that VLAs aren't supported in C++. And I know some of you are saying, yeah, C++ does have variable length arrays. They're called vectors. And you guys, that's not the same thing, and you know it. We're talking about arrays here, not vectors. But the point is that if I write this code with VLAs, then I can't just later come and move it into one of my C++ programs. And I find myself doing that often enough that I try to steer clear of things that are significantly different between the languages whenever I think of it. So if this is not the way that I usually do it, then how should we do it? Okay, well, the classic approach, it's maybe a little more cumbersome, but here, let me show you how it works. So let's come down here, and what we're gonna do is, let's start by we're gonna take off the columns here, and we're going to make this an array of pointers. So now what we have is we have an array of rows. Remember that I said you want to think of a matrix as an array of rows? Well, now that's exactly what we're going to be doing. We're going to take advantage of the fact that arrays and pointers are almost the same thing, and we're going to make an array of pointers that is as long as the number of rows we have. And then for each row, we're actually going to allocate that row on the heap, something like this. And let's call calloc and matrix rows and size of int. Okay, so what we're basically just saying is, hey, I want this number of integers, the number of rows, and actually I got that wrong. It should be cols, sorry. Okay, so the number of columns, basically as long as each row should be, that's the number of columns, times the size of int. And so that's going to allocate us a new row. And then everything else in here can stay the same. We might at some point want to check to make sure that calloc didn't return null. I'm not going to do that today just to keep this example simple, but in a real program, you might want to check to make sure that you didn't have memory allocation errors. They're rare, but they're a pain when they come up. So now that we've changed our declaration, let's also take a look at what's going on in our print matrix function. So we can come up here. We still need to tell it how many rows and columns, but what I'm going to do is change this to a double pointer here. And now things should work. Okay, so now we should come back here and we should be able to compile and run. And more or less we have the same result, except you will notice one thing, and that is that our size of changed, right? It used to be 80, now it's 40. Why is that? Well, now folks, we have, if you look down here, we have an array of pointers, and that array is 5 elements long, and pointers are each 8 bytes, at least on this machine. So an array of 5 8-byte pointers is going to be 40 bytes total. So note that things are being laid out differently in memory. So this changes how things are internally. Like before, our matrix was just one block of bytes, and that's not the case anymore. Now the allocator could have given me rows that were all over the place. I mean, it probably didn't, but it could have. Okay, so now I want to also look at one other variant, because like one thing that's weird here is this is a local variable with a bunch of heap allocated dynamic memory attached to it. So usually what I end up doing, if I want to make this so it doesn't just go away after I'm done here, is I might instead, I'll leave this just for reference, but I might take this off as well, make this a double pointer from the beginning. And then here, what I'm going to do is just calloc my array of rows as well. And here we're going to say matrix rows and size of int pointer. Okay, so this is going to allocate for my matrix. It's going to allocate an array of rows that has this many rows, and each element is an int pointer. So let's get the size of an int pointer. So now my entire matrix is allocated on the heap. This might be a little slower because we just added an extra call to calloc, but for now I'm going to assume that's okay. But now the point is that my whole matrix is on the heap. And this comes in handy. This is basically how I would do it if I was allocating a matrix that I was then going to return from a function. Like say I have a function that's like a create matrix function, and I want to create it and then return it to other functions for them to use. This is how I would do it, because now I can just return the pointer, okay? Now, of course, anytime that we allocate things on the heap, we typically want to make sure we're in the habit of cleaning things up. Okay, so what I want to do here is just come down and clean up our memory. Let's add another loop here. And what we're going to do is we're just going to come in here and free each row. And then after we're done freeing all the rows, we're going to free our matrix, our array of rows, our array of pointers, right? Oh, and I said I want row. Now keep in mind that order matters here. So if you free the matrix first, if you were to put this up here at the beginning, well, the problem is you're freeing all these pointers, you're basically releasing them before you try to release what they point to. And so your program might crash in unexpected ways if you do this. It depends a lot on how your allocator works, whether you will crash or not crash, but it's not safe. So make sure that you free the rows first and then free the matrix. Okay, so this should work, but again, let's just make sure. So we're gonna compile it. And we're going to run it. And it does work, except notice again that our size changed once more, okay? Because now our matrix isn't an array of pointers, it's a pointer to a pointer. And a pointer is just 8 bytes. And so keep an eye on stuff like that because the size of behavior is changing. I have a video on this and how, size of a pointer is always 8 and it sometimes trips people up. But I just want to point that out because this causes a lot of pain and suffering for new programmers. Okay, now as I mentioned before, this stuff will work on both C and C++. So let's discuss some minor differences here. Okay, so let me just take this. I'm going to take this whole thing and we're just going to copy it on top of my matrix2.cpp file. Okay, so now we are magically over in C++ land. Now, if I'm here and I try to compile it, you're going to notice that I get some errors. Okay, so let's just talk about how this is going to work differently over here. So one thing that's going to be different is calloc. So calloc returns a void pointer in C because we're used to using malloc, calloc, realloc, and free. Void pointers being assigned to some other type of pointer. No big deal. You don't need a cast. In C++, they say, yeah, we want to cast. Okay, so here all I have to do is say, cast this to an int double pointer and cast each of these to an int pointer, and we should compile just fine. So this is one way to solve this problem. The code will run, let's just make sure, but it runs just fine. But some of you are out there saying, this is not very idiomatic C++, and you're right, it isn't. This is kind of the more C-style programming. That's fine. It works perfectly in C++, but we could also do this, and many in the C++ community would prefer that you do this using new and delete. So let's just do that just so you can see how this works. Is that way we don't need a cast over here. We can instead just, I'll keep this around just so you can see it, but we can instead just come out here and say, this is going to be a new int pointer of size matrix rows. Okay, so that's going to take the place of our calloc. And then down here, we can do the same thing here and say, new int matrix calls. Okay, so now we've done that. Now we, of course, you don't ever want to mix news and freeze because there's always the possibility that they're doing things differently under the hood when they're allocating the memory. So instead here, we would want to use the delete operator for our rows. We have the square brackets here because we are deleting an array. So that just reminds it that we're not just deleting one object that's pointed to, we're deleting a row of them. And now this should work here. Let's just make sure. Okay, so we're in good shape. Now this is definitely looking more idiomatic all the time. We could of course go further and use vectors, use standard vector, but this is a video about arrays, so I'm gonna stop here. We could make a class to encapsulate this matrix and add bounds checking and handle allocation and cleanup in constructors and destructors, and that would actually be kind of nice in this case. So let me know if you'd like to see that in a future video. But today our time is up. Like this video if you enjoyed it, subscribe to the channel if you don't wanna miss the next one. If you really like the channel, check me out on Patreon and my courses. And until next week, I'll see you later.